Okay, everybody, so today we're going to look at graphical analysis of motion. So how can we take motion and describe it using graphs? The first thing we need to know is about slope, right? So we're going to use a basic graphing model here, and that model is the slope of something. And if you remember, slope is rise over run, or it's the change in y over the change in x, right? How far up did I go divided by how far over I went, right? That's the slope. Let's take a look at velocity, right? So we saw in the last set of notes that velocity is the displacement divided by time, right? It's my change in position divided by a change in time. Well, this looks a lot like my slope, right? Slope is a rise over a run. So here, if I use this formula, right, who's playing the role of the slope in this case? Well, it's going to be the velocity, right? Velocity and slope kind of go together in this formula. Who gets to play the role of the y-axis or of the rise? Well, the rise was up here on top in the numerator of this fraction. Over here I've got this delta x. This delta x is my displacement or my change in position. So displacement gets to play the role of the rise. Who gets to play the role of the x-axis or the run? Well, that's going to be time, right? So time's down here on bottom. That's the rise over the run, displacement over time. So what does all that mean? Well, it means that if you're given a displacement versus time graph, right, this is a graph where displacement is on the y-axis and time is on the x-axis, to find the velocity of the object during a specific time interval, all we need to do is find the slope, right? Slope is the rate of change of something, right? How steep a line is on a graph is how quickly it's changing, right? So the steeper it is, the faster that graph is changing. And the rate of change of displacement is velocity. So let's take a look at this, right? So I've got a displacement versus time graph. So displacement is on the y-axis, time is on the x. And what is the velocity of the object from 0 to 3 seconds? So from 0 to 3 seconds is this part of the line right here. Well, all I need to do is I just need to find the slope, right? So how far up did it go divided by how far over it went. So the change, the rise here, right, is 30 meters. And the run over here is 3 seconds. So 30 over 3 is 10 meters per second. That's going to wind up being the velocity, right? So the velocity is just the slope. What is the velocity of the object from 7 seconds to 8 seconds? So again, we just look at the slope, right? So this is a displacement versus time graph. So from 7 seconds to 8 seconds, we're looking at this piece right here. Well, a horizontal line on a graph has a slope of 0. It's not changing, right? So there is no rate of change. So the final position is 90 meters. The initial position is 90 meters. I divide that by the number of seconds, but 90 minus 90 is 0, right? So I get 0 over 1 in this case, and that's 0 meters per second. So what does a velocity of 0 means? Well, it just means that the object's standing still, right? It's during this time interval, during this 1 second time interval, it's not moving. What is the velocity from 8 to 10 seconds? So from 8 to 10 seconds, well, look, so now I've got this line going down. This is going to wind up being a negative slope, right? So I'm going to have a negative velocity. So I take the final velocity minus the initial, 0 minus 90. I divide it by the time interval. In this case, it's 2 seconds. So negative 90 over 2 is a negative 45 meters per second. And so the answer is negative, and that shouldn't be a surprise because the slope is considered to be negative. And this just means that the object's moving back the other way, right? We talked about positive and negative signs with velocity in the last set of notes. So in this case, the object moves back the other way. And that should make sense, right? Think about it. This is a position graph, right? So there's a displacement on this axis. I start off at 0 meters, I end at 0 meters. So I had to go forward at one point, I had to come back at another in order to end back up where I started. Let's look at another example, right? So it's very important that you're able to look at graphs and explain its motion in detail. So these graphs can be very conceptual in nature. So let's look at the time interval from 0 to 9 seconds. So what's happening? What is the slope doing from 0 to 9 seconds? Well, down here, the slope is a lot flatter than it is up here, right? So that means that the slope itself is actually increasing, right? I'm going from a lower slope up to a higher slope. Well, that means the velocity is increasing, right? So I have an increasing velocity there. What about from 9 to 11 seconds? Well, from 9 to 11, now I'm looking here, there's no slope, so the velocity is 0. Then I'll look at 11 to 15. What is the slope doing? Well, the slope is positive, and it's not changing, right? It's at a steady angle there, just going straight up, right? So that means I have a constant positive velocity. Let's look at 15 down to 17. What does the slope do? Well, the slope is constant, and it's negative, right? I'm going from here up to there, right? From there down to there. It's constant and it's negative, right? So the object's moving backwards at a constant velocity. I can get all that information about what's going on in those different time intervals from one graph. Let's look at another model, right? So in this case, slope again is rise over run, right? We know acceleration is a change in velocity over time. Well, again, this looks a lot like slope, right? It looks like a rise divided by a run. In this case, who gets to play the slope? Well, it's going to be it's going to be the acceleration. Who gets to play the role of the y-axis or the rise? Well, the rise is up here. It's a change in velocity, right? So velocity gets to play the rise. Who gets to play the role in the x-axis or the run? Well, again, it's going to be time, right? So what does that mean? So it means if you're given a velocity versus time graph, again, where velocity is on the y-axis and time is on the x-axis, to find the acceleration of an object, you just need to find the slope. Okay, so here's a different graph, right? It might look similar to the other graph, but I don't have displacement over here anymore. Now I've got velocity, right? So this is a velocity versus time graph. What is the acceleration from 0 to 6 seconds? Well, that's this first time interval here, right? And I just find the slope of that thing. So the slope of that is going to be 10 meters per second squared, 10 meters per second squared. What is the acceleration from 6 to 9? Well, from 6 to 9, I'm looking at from here over to here. The acceleration is 0, right? It's not accelerating. So what can we say about that, right? So an object that has 0 acceleration is going to have a constant velocity, right? Acceleration is a change in velocity over time. So if there's a 0 acceleration, the velocity is constant. What is the acceleration from 14 to 15 seconds? Well, from 14 to 15, we're down here, right? So I do rise over run, I get a negative 10 meters per second squared, right? Because that slope is downward. A negative acceleration is sometimes called deceleration. In other words, the object is slowing down. An object can also have a negative acceleration if it's falling and speeding up, right? It could be confusing, right? So be careful, make sure you understand why the negative sign is there. Is it a negative acceleration because it's slowing down, or is it a negative acceleration because it's speeding up in the negative direction? Right? Those can both happen. Conceptually speaking, what is the object doing during the first time interval, or during the time interval from 9 to 13 seconds? Well, from 9 to 13 seconds, right, we're looking here. So the slope is actually increasing, right? It's increasing, but it's increasing in the negative direction, right? It's getting steeper, right? But it's getting steeper going down, okay? So it's getting steeper going down. What does that mean? Well, that means that the velocity is slowing down and a greater change, with a greater change each second. So the deceleration in this case is getting larger even though the velocity is decreasing. The velocity goes from 60 to 55, a change of 5, then from 55 to 45, a change of 10, then from 45 to 30, a change of 15, then from 30 to 10, a change of 20. So do we see how the change gets larger as the velocity gets smaller? Right? The change gets larger as the velocity gets smaller. The other basic graph model we can look at is area. So instead of looking at slope, we can look at the area of a curve. And now we know that for like a rectangle, right, area is just base times height. Okay. So algebraically, let's try to make some sense out of this, right? So if area is base times height, and I know velocity is displacement over time, I could rearrange this to say, well, displacement is time multiplied by velocity, right? Displacement is time multiplied by velocity. I get there just by multiplying both sides by time, right? If I multiply this by time, time cancels, and then if I multiply this by time, I get times time velocity. So who gets to play the role of the base in this case? Well, the base is going to be time, right? Area is base times height. Area equals base times height. So who gets to play the role of the height? Well, it's going to be the velocity. What kind of graph is this? This is a velocity versus time graph, right? So if I have velocity on the y-axis and I have time on the x-axis, then the area under that graph is going to wind up being the displacement. Okay, so what do I mean by that, right? Well, let's look at, this is a velocity versus time graph. Let's look at the time interval from 0 to 5 seconds. How do I find the displacement? Well, the displacement is going to be the area, right? And so I'm talking about this area right here. It's the area down to the horizontal axis, okay? And in this case, this is a triangle, right? So area is 1/2 base times height, okay? 1/2 times the base. I have a base here of 5 times a height of 35. I get 87.5 meters, right? So 87.5 meters. What is the displacement during the time interval from 8 to 12 seconds? Again, we're going to look at the area, right? During this time period, we have a triangle and a square, right? So let's look at that. There's a square there, and then there's a triangle there. So I need to figure out those areas separately, right? The area of a square or a rectangle is base times height. In this case, it's 4 times 35, or 140 meters. The area of the triangle here is 1/2 base times height. I get 120 meters there. So I have a total displacement during this time interval of 260 meters, right? It's the area all the way down to the horizontal axis. Let's look at this model again for area, but now let's look at this equation for acceleration. So area is base times height. We know the acceleration is a change in velocity over time, so by multiplying both sides by time again, I get the velocity to equal the time times the acceleration. So who gets to play the role of the base here? The base is still going to be the time. Who gets to play the role of the height? The height is the acceleration. So what kind of graph is this? This is going to be an acceleration versus time graph. Acceleration on the y-axis, time on the x-axis. And then who gets to play the role of the area? Well, the area is going to wind up being the velocity, or at least the change in velocity. Let's look at this for a second, right? What is the velocity during the time interval from 3 to 6 seconds? So this is an acceleration versus time graph. I'm looking from 3 to 6 seconds. I'm looking at this area here, right? So this is the area from there to there, all the way down to the horizontal axis. If I find the area here, that's going to give me the velocity, or at least the change in velocity. And so that's going to be 3 times 6, or I get 18 meters per second. So just to summarize, there's going to be 3 types of motion graphs. We have a displacement versus time graph, a velocity versus time graph, and an acceleration versus time graph. Notice that all these graphs have time on the horizontal axis. That's the one down there on the bottom. That's always going to be time. And there's 2 basic graph models we can look at. We can look at the slope, or we can look at the area. So let's look at those 3 graphs. Here's my displacement versus time, velocity versus time, my acceleration versus time. So on the displacement versus time, the slope is the velocity. On the velocity versus time, slope is the acceleration. But I can also take the area to get me back here to find the displacement, right? So velocity versus time, slope is acceleration, and the area is the displacement. And then on an acceleration versus time graph, the area is going to wind up being the change in velocity. Okay, that's really what you need to know. Comparing and sketching graphs, right? So one of the more difficult applications of graphs in physics is when given a certain type of graph and asked to draw a different type of graph. So let's look at this one. This is a displacement versus time graph. We know the slope is the velocity. List 2 adjectives to describe the slope. Well, I know that the slope is constant, right? The slope is not changing, right? It's got one steady slope all the way up. And I know that the slope is positive. Okay? Well, how do I graph that on a velocity versus time graph? Well, it needs to be positive, so it needs to be above the horizontal axis, and it needs to be constant. It needs to be flat. Okay, it can't change. Let's look at an example here. So I have a position versus time graph, and there's 3 separate lines here, right? So let's describe those 3 lines. The first line, the slope is constant, and it's negative. Okay, so if the second line, the slope is 0, right? There's 0 slope on a flat line. And on the third line, the slope is positive, and it's constant. How do I graph that on my velocity versus time graph? Well, the first part is constant and negative, so it needs to be below the horizontal axis. The second part, the slope was 0, so it needs to be on the horizontal axis. And the third one, the slope was positive and constant. It needs to be flat and above the horizontal axis. Notice that this one is further down below the horizontal than this one is up, right? So this distance here is smaller than this distance here. And it has to do with the slope, right? This slope is steeper, even though it's negative, it's steeper here than it is there, right? So this one, because it's steeper, needs to be down lower. A little bit of graph matching for a second, right? So what is the slope doing? Well, let's look at is this velocity versus time graph? The slope is increasing, right? So that's going to be a increasing acceleration. Okay, that's all. So if you have any questions, please let me know.